So mass spectrometry, we're coming into this right at the end of our course following the modules on infrared and NMR spectroscopy, and the bulk of this module is going to indeed be about mass spec applied to organic molecules. But we also kind of skipped over the discussion of it that could have been all the way back right at the start of the very first module. So I'm going to make amends for that now and just have a fast chat about mass spectrometry. So here is a diagrammatic representation of a mass spectrometer. It's completely hand drawn because I couldn't find a free piece of art online that where I could actually determine who the original person was, as is often the case. There's so many of these pictures there that are identical that everybody except one has nicked. But anyway, here is a mass spec. So essentially you have a guiding area here, a tube here that goes through this purple thing. That is how I'm depicting a magnet, and that magnet will bend the path of the appropriate things to come down here. Okay, so we study with this atoms, we study molecules. Those molecules can be elemental or they can be compounds, and we'll treat all of those as we go through the module. Essentially, we're going to vaporize our sample, and so here it is here. I had great issues with spelling of vaporize, so I decided to combine the British and the US spelling. So anyway, we've got a vaporized sample here that can be an atom or a molecule, and that the sample can originally be a gas, or it can be a vaporized liquid, or even a vaporized solid. So we allow that to enter into this first tube, whereupon it enters the so-called ionization chamber. And what happens there is it gets ionized. Essentially, the most common type of mass spec, and the one that you would be expected to repeat on A level, is so-called Electron Impact Ii, in which your vaporized sample is just bombarded with these really high energy electrons that serve to knock at least one electron out of your molecule or atom. We're just going to assume the case in which a molecule or an atom has one electron knocked out of it. Now, there's an interesting alternative to electron impact called chemical ionization. The whole idea is that by the time that your molecule or atom leaves this chamber, you want it to be a cation. So of course the normal way to do it is you bombard it with electrons so it has an electron knocked out of it to become a cation. But chemical ionization, in which you're not bombarding your sample itself, you're bombarding ammonium, and the proton gets transferred from the ammonium to your molecule, thus turning your molecule or your atom into a cation itself by having on the H+. A level is just electron impact. Anyway, so then your poor little vaporized sample that has now had an electron knocked out of it comes out the ionization chamber, and it gets accelerated by an accelerometer, just some charged plates that speed it up towards the magnet. Okay, so there's our sample here, right? Vaporized sample, ionized. I should have changed color, but I didn't. Anyway, so here's the sample come along here, goes into the magnet, and ideally it will curve around the magnet. And I apologize, but it was much easier just to draw these things freehand. So it curves around the magnet, enters into this tube here. The deflection is the fancy A-level name you'll need to recognize for that. Comes down here and hits the detector where it is detected. And this detector is picking it up in terms of its mass over its charge. Now, we usually assume, at least for A-level, that the charge of our cations here are +1. So essentially the detector is arranged in terms of mass. But we say the fancy way to say it is mass over Z, mass over charge, which as far as we're concerned, Z is always +1. Now, the fun thing about this is that it's all to do with turning things into cations and then getting the appropriate amount of deflection. So let's say that one of your vaporized molecules makes it through here without being ionized. So it's tootling along, because of course it's not going to be accelerated, tootling along, will not be affected by the magnet, and so will just keep crashing up and won't be deflected. You also see this phenomenon if the cation that you make, so your species is in there and it's turned into a cation, but if it's so heavy that the magnet isn't strong enough to curve it, and so it will also crash, like we say, into the top part of the magnet. Now, the opposite of that is, of course, if you have light cations. So here we've got a cation and it's happy, but it's so light that the magnet has a massive effect on it and smashes it into the side. Or if you've got extra charge cations, let's say that your molecule is now moving along, but it lost 2 electrons, so it's 2+, so now again it's going to feel the magnet a lot more and will smash into the side. The point being that you can fine-tune how strong your magnet is, so the extent of the deflection, so you can pick up just the right types of cations down here, just the right sizes of cations. You can set it so that it won't pick up the 2+ species. You can set it so it won't pick up light ones, it won't pick up heavy ones, and so forth. Now, the real beauty, however, of the mass spec, and where it first achieved notoriety, at least a form of it achieved notoriety, and its main reason for use today, is that we've talked about our cation coming around here being deflected down here. Well, different massed cations, different size cations, will be deflected differently. So let's say that now my vaporized sample consists of 2 cations, one that's a blue cation and one that's a sort of gold cation. So they're traveling along here, hit the magnet, and then the gold one will start to be deflected a little bit more differently by the magnet, as you can kind of see here, and ends up hitting the detector in a different spot. Thus our detector can detect that there were 2 types of cations in there. So that's the fundamental idea of mass spectrometry. We take a molecule or an atom, we turn it into a cation, and then we can watch it coming through here. If it's the right size cation, so it makes it through the deflection without hitting the sides, then we can pick it up. And it's particularly useful for separating cations of different masses.